Hi, welcome to A Tiny Bit of Combinatorics. In other videos on this channel, we'll be talking about the binomial distribution and the Poisson and Gaussian statistics. Before we jump into those topics, there are a couple of quick mathematical results that are useful to know. So we'll obtain those quick results here in this video. Both of these results are going to involve the following situation. So we have n distinguishable objects. Here, they're distinguishable because we've numbered them 1 through n. And we're going to ask two questions. First, we'll put the n objects in a line. How many different orders can we put them in? And then second, let's choose a subset of m of these n objects. How many distinct subsets of m objects could we choose if we ignore the order in which they are chosen? The answer to the first question will help us get the second. Okay, so let's start with the first question. How many ways can we order the n objects? So let's start by choosing the first object. There are n objects to choose from, so that means there are n possible ways to choose the first object. Okay, now let's choose the second object. There are n-1 remaining objects to choose from, so this means that there are n times n-1 possible ways to choose the first two objects in the sequence. Likewise, there are n-2 ways to choose the third object in the sequence, and this process continues until there is only one object left, which will be the last in the sequence. So the number of possible orderings is n times n-1 times n-2, and so on down to 3 times 2 times 1. This quantity is written as n exclamation point and is called n factorial. Okay, so let's look at some examples. So for one object, we have 1 factorial, which equals 1, and there's one order that we can put one object in. For two objects, we have 2 factorial, which equals 2, and there are 2 orders in which we can put 2 objects. For 3 objects, we have 3 factorial, which equals 6, and the 6 different orderings of 3 objects are shown here. So it's good to know that n factorial grows quite quickly with increasing n. So 4 factorial is equal to 24, 5 factorial is equal to 120, and 11 factorial is equal to 39 million and change. Okay, so now let's move on to the second question. So let's choose a subset of m of these n objects, paying no attention to the order in which the m objects were chosen. So the question is, how many of these different distinct subsets of m objects can we choose? So here we'll represent the objects that we choose in light green. Okay, so let's start with some concrete examples. Let's start with m equals 1. So we choose one object out of the n. There are n possible sets of one object that we could choose, so the answer is n. Now let's look at m equals 2. So we choose the first object. There are n ways to do this. Then we choose the second object. There are n-1 remaining objects, so that means there are n-1 ways to choose the second object. So it might look like the answer is n times n-1. But we said that we wanted the number of distinct subsets, not paying attention to the order in which the objects were chosen. So let's say that we choose object 3 and then object 17. This gives the same subset as if we had chosen object 17 and then object 3. So both of these actions give the same subset, so we want to count them as only one. The situation is the same for whatever pair of objects we chose, so we've overcounted by a factor of 2. So the correct answer is n times n-1 divided by 2. Okay, now let's look at m equals 3. So there are n ways to choose the first object. There are n-1 ways to choose the second object. There are n-2 ways to choose the third object. So those factors multiply to give n times n-1 times n-2. But Like last time, we've overcounted. So take the subset that we get by choosing objects 2, 19, and 22. We get the same subset by choosing these objects in any order. So we could choose the objects in the order 2, 19, 22. We could choose 2, then 22, then 19, etc. Now, we know that the number of ways to order 3 objects is 3 factorial, which equals 6. So we've overcounted by a factor of 6, and our final answer is n times n minus 1 times n minus 2 divided by 6. Okay, so let's generalize to any m that's less than or equal to n. So for each object that we choose, we get a factor of the number of objects that we had to choose from at that step. So we get n times n minus 1 times n minus 2 all the way down to n minus m plus 1. So there are m of these factors, and the first one is n, and the last one is n minus m plus 1. And it's very useful to note that this is the first m factors in n factorial. Okay, so now let's rewrite that expression. So it had m factors, which started with n and ended with n minus m plus 1. Let's use the expressions for n factorial and n minus m factorial. So n factorial is n times n minus 1, etc., down to 1, and n minus m factorial is n minus m times n minus m minus 1, etc., down to 1. We thus get that our expression n times n minus 1 times n minus 2, etc., down to n minus m plus 1 is equal to n factorial divided by n minus m factorial. Okay, so we're almost there. We still need to divide by the overcounting factor that we ran into earlier. So this was the number of orderings of our choices of m objects. And we know from before that this is equal to m factorial. So the number of distinct subsets of m objects that we can choose out of n, ignoring the order in which they are chosen, is n factorial divided by n minus m factorial divided by m factorial. Now, we'll mention a couple of points about this second result. First, this expression is useful and has some dedicated notation. So we write this as n and m in a big set of parentheses, and it is read as n choose m. Second, when we choose a subset of m objects out of the n, we leave behind a subset of n minus m objects. So we can look at this procedure as separating the n objects into two groups, one of m objects and one of n minus m objects. So the number of distinct subsets of m objects should be the same as the number of distinct subsets of n minus m objects. So n choose m should be equal to n choose n minus m. And we can see that mathematically by writing out the expression for n choose n minus m. So we get n factorial divided by n minus m factorial divided by n minus m factorial, which is equal to n factorial divided by m factorial divided by n minus m factorial. And that's just n choose m. Okay, so here we have seen two useful results. First, the number of ways that we can order n objects is n factorial. And second, the number of ways that we can choose m out of n objects, ignoring the order in which they are chosen, is n choose m, which is equal to n factorial over n minus m factorial divided by m factorial. So these results will come in handy when discussing the binomial, Poisson, and Gaussian distributions. Thanks.